Hi, I'm Maria Gallucci. I'm a reporter at Canary Media, and I'm here today with Pete Johnson, the co-founder and CEO of Koloma, a geologic hydrogen company. Koloma has raised over $350 million in recent years from Coastal Ventures and other prominent VC funds to tap into what has largely been an untapped energy resource, naturally occurring hydrogen, which is sometimes also called primary hydrogen. So Pete, can you help us set the stage, give us a bit of the history of geologic hydrogen, and then kind of a bit about your own history, how you got into this space?
I got into the hydrogen space about 12 years ago when I founded a company called Monolith Materials. That's a methane pyrolysis business. And, there's lots of ways we make hydrogen. We can make it from natural gas in a few different ways. We can make it from electricity. I ran that business for 6 years. I'm an engineer by training, and then I got pulled in to work on investing with an oil and gas private equity firm, looking at lots of different ways to invest in hydrogen. And I was sort of going about my own merry ways, and my friends from Breakthrough Energy Ventures reached out to me, and they said, "Hey, we want you to come help us found and run a business in the geologic hydrogen space." And my first reaction was like, "Go away, guys. I only do serious things. I've never heard of this before." And so, it's interesting. Like, 3 years ago, nobody was talking about this. And now you have like the Times, the Journal, like everybody's publishing articles, geologic hydrogen. So it's become a really big topic of recently. But let me tell you, my first reaction was, I don't really believe this. And then I started to look into this. So let me talk a little bit about the science of this and where this comes from, and then kind of the history. So there's a reaction that happens underground in the earth where water interacts with iron-rich rock. And the water oxidizes the iron in the rock, and that frees up hydrogen gas. And that reaction happens, probably a lot faster than oil and gas reactions happen, but it's still slow on sort of modern day times. Think thousands of years as opposed to millions of years. But there's hydrogen seeping out of the ocean in the mid-Atlantic Rift. There's hydrogen coming out of steam vents, Iceland. There's hydrogen seeps identified on every continent of the planet. So we know that the Earth produces vast amounts of hydrogen with this reaction that happens under the ground. And that science is really well accepted. That's a process called serpentinization. And there's really no debate that that's been going on for a time immemorial and will go on forever. The bigger question is, are there places where hydrogen is being formed underground but then being trapped and accumulating the same way that methane is helium? And that's really the question that needs to be answered with everybody who's in the geologic hydrogen space. Is not, does hydrogen form? It's the question of, does hydrogen accumulate, and can we find it? From a historical perspective, a group of people drilled a water well in Mali, Africa in the 80s. And there was an accident that they drilled this well. They didn't find anything. They didn't find as much water as they hoped, but the gas started coming out of this well, and the gas lit on fire, and it didn't look like methane gas. It was an invisible flame. And they realized they were pulling 90%-ish pure hydrogen out of this well. So this was a long time ago, and not a lot of people paid attention to it. But, for a long time, they've been producing electricity in Mali, Africa, using hydrogen flowing out of the ground. Now, that's not a giant asset. That's not a huge reservoir. It's pretty small, but it kind of set off a lot of interest in this space. And so as you kind of think about, why is this suddenly interesting now? Well, part of it is that it hasn't been that long since people really started turning their attention into finding really interesting ways to do business with hydrogen. So this is just kind of sequentially happening after that.
Yeah, great. Thank you for that. And I'm curious if you could talk a bit more about sort of what about naturally occurring hydrogen kind of makes it difficult to identify, or, why haven't we been able to kind of tap into it in the way that, say, we have with oil and gas?
Yeah. So, it's important to remember that we haven't really been in the oil and gas business that long as humans. Like, we started getting into oil and gas like 150 years, right? Somebody found some oil in Pennsylvania, and that started people realizing, okay, there's this source of energy on the ground. And so now we're really good at finding that oil. Haven't been after it long. Geologic hydrogen is formed in regions that are not typically contiguous with oil and gas locations. So if you were looking for hydrogen, you're not going to go out and drill in the Permian Basin Marcellus Shale. You're actually going to be drilling in totally different places, looking at completely different source rocks. Because of that, there are not a lot of wells drilled or geophysics studies done in the regions that are the most prospective for geologic hydrogen. We have a lot of data that we've purchased and acquired through various means of wells that have found hydrogen, but almost all of them were an accident, right? I was drilling for oil or gas, or helium, or water, and I found some accumulation of hydrogen. I'm not sure what it means. We have a lot of that data, but most of those are right on the fringes of the most interesting places where you'd find hydrogen. So right now, Koloma is running, the world's first multi-well intentional exploration campaign looking for hydrogen. There's going to be a bunch of other groups like us that are going to come in and start doing this. But you have to think about it. It's like when you're not exploring for something, finding it by accident, if you're drilling in all the wrong places, is not very likely.
And I wonder if you could talk more about sort of what's driving Koloma to do this work of intentionally looking for these resources. Obviously, there's a lot of interest, as you mentioned, in sort of hydrogen. What would it mean for climate, for the kind of the broader energy transition if we really were able to fully produce this geologic hydrogen?
So before I decided to jump into this, so just to be totally clear and upfront, I am not a geologist. I am not a reservoir engineer. I'm not a drilling engineer. I am a topside engineer. My career has been in developing technology and processing gas and producing gas. So I know the hydrogen markets and the hydrogen customers a lot better than I know geology. And when I first started thinking about this, I kind of did the math and I thought about what changes if we can find hydrogen that costs the same on a volume basis as natural gas, right? And, we don't know that we're going to be able to approach those costs, especially early on as, more and more capital is going to exploration. But from a long-term perspective, it's very viable to believe that you could produce hydrogen on a per volume basis at roughly the same cost that we can produce methane. And what changes if we can actually do that? This would be a primary energy source, meaning that you're not converting electricity to hydrogen or converting natural gas. You're pulling this out of the ground the same way we pull gas, oil, coal, and uranium. Be the world's first new primary energy source in 100 years. Right. And what changes? If you can pull hydrogen out at those kinds of competitive, you're talking about sustainable aviation fuel for about the price of kerosene, carbon free. You're talking about ammonia-based fertilizers that's cheaper than anything that we can produce today, fossil-based ammonia. You're talking about base load, demand response, load following power for 7 cents a kilowatt. Holy grail number that is on the level of sort of the impact of fusion. So as I started thinking about, well, if this is really as big as we think it could be, and we can deploy the exploration tools we have, modify them a little bit to really have the same kind of level of success and probability of success that you have exploring for oil and gas eventually, I mean, this will be kind of a skeleton key in decarbonization where you can really accelerate decarbonization because of the price point that I think you could achieve with this as a primary energy source. So I was all in. There's a lot of risks here, but decided, look, like this is a really big swing, but from an impact standpoint, I don't know that there's anything else out there that could have as big of an impact. That's not to say that it's a done deal or it's a sure bet. Like there's a lot of risk here, but if it works, it's going to have a huge impact on the way we're thinking about energy transition.
And given that Koloma is kind of entering into kind of a relatively new space, doing something relatively new, how do you go about building a team for that? What kind of skills or expertise have you brought on board? You mentioned some overlap with oil and gas. Maybe you could elaborate on that.
Yeah, so maybe I'll give you a case study here. So my two technical leaders in my business, my co-founder, Tom Dara, who was a professor of geochemistry and geology at Ohio State, and basically was running the world's leading testing lab looking at oddball gases all over the world. Developed a bunch of artificial intelligence tools and satellite imagery-based tools, and is essentially the world's leading expert on this kind of reaction in this kind of source rock, and has built a bunch of these sort of AI machine learning tools that allow us to access broader sets of data and really sort of enhance the power of data analysis. I combined Tom with our head of exploration, whose name is Tim Chisholm, who came from Hess and was actually the guy responsible for finding the Guyana play, which is one of the world's last giant oil. So like classic example of, great science, great data meets oil and gas exploration. And so if you look at my team, I've got data scientists, I've got geologists, I've got reservoir engineers. It's like a combination of AI, data science with oil and gas. And we try to tap into mining and geothermal because geologic hydrogen shares some similarities across the board. But, we're taking oil and gas professionals who know their trade and really skilled at it, who want to deploy it, looking for the world's next primary energy source that's carbon free. And it's a great place to put oil and gas talent that the U.S. has to work in the energy transition.
It's interesting. It sounds like, of course, you're not just bringing the people over, but also maybe some of the tools and technologies, as you were mentioning, that they were developing. Could you talk a bit more about sort of the tech side of it, or how you kind of go about looking for and eventually producing geologic hydrogen?
Yeah, and it mirrors the discussion about skill sets, right? We have a bunch of data-driven AI tools and other things that we are working on specifically for geologic hydrogen and source rock analysis, system analysis. And then we pair those with, shooting geophysics, 2D size, 3D size drilling wells. I mean, these are things that the oil and gas industry has owned over the last 100 years in the mining industry. So it's kind of a combination of new tech that we're developing and data-driven tech plus the soul tech. And I'll give you an example. When hydrogen seeps out of the ground, it leaves kind of a scar on the land, what's called an ovoid or a ferry circle. And Koloma has developed the technology where we can use different spectral satellite imagery, and we've identified every seep on the planet using AI image recognition. Finding a seep doesn't guarantee that you're finding an accumulation, but it sure increases your chances. So that's a use of kind of a new tool in satellite imagery to go help be in the right locations. The next step on top of that is coming in and using oil and gas tools, shooting seismic, understanding what the subsurface looks like under that to figure out if there's any traps. And so again, it's a combination of new things and oil and gas tools, mining tools.
And you talked earlier about the big potential, how transformative it could be for the energy system, for the climate, if we could unlock geologic hydrogen. I wonder if you could elaborate a bit more on sort of what's needed, what steps have to happen for it to become cost effective and kind of become a competitive energy source.
Well, I think the big first step on hitting the cost targets you need is that we've got to get better and better at exploring for, right? I mean, you have to account for exploration cost into the cost of production the same way that we have to account for R&D costs in the cost of drugs, right? Like if medicines were just about the manufacturing costs, they'd all be really cheap, but there's hundreds of millions of dollars that go into developing the medicines. Exploration is the same. So you have to believe that as Koloma and a number of other great groups start launching into this exploration, it's going to take a bunch of misses before you find the really big plays. So you might find a small play here, a small play there, and the rock's okay, and a little bit of hydrogen comes out, and your costs are higher. And this all comes down to how much gas can you get out of one well, right? And if you can find the absolute biggest plays, you're going to get really, really low costs. But it'll take years and years of exploration to find the Permian Basin equivalent of hydrogen. So our costs will come down as we get better and better at finding things and have fewer and fewer dry holes. And that's just typical exploration.
And I know a challenge for all forms of hydrogen, sort of regardless if it's natural or, man-made, face a challenge of getting the fuel, getting the energy to where it's ultimately needed, which adds a lot of operational costs. How do you think about that in the context of geologic hydrogen and how that kind of fits in?
Yeah, so hydrogen is expensive to move, right? And that's because, look, you can move it by truck as compressed gas, you can move it by truck by liquid, or you can move it by pipe. And those are the direct ways to move it. And the cheapest way to move hydrogen is by pipeline. We have 1,600 miles of hydrogen pipeline in the country, and we know how to move hydrogen by pipe. but it's hard to permit pipelines, and there's a lot of sort of fixed costs involved in that. And so the great thing about hydrogen is if you look at what hydrogen is used for, most of the uses of hydrogen are to produce valuable liquid forms of energy, like sustainable aviation fuel and ammonia, and sometimes to produce power or use it in steel. And the experience is that as we've gone out and we've talked to people who want to develop hydrogen-based asset, and we've said, hey, we're exploring in this region over here, and we think there could be a lot of hydrogen. Would you be interested in moving the site that you're trying to develop over closer to us, so that if we are right that there's hydrogen, you'll be sitting on the lowest cost hydrogen anywhere in the world? And the answer has been affirmative in every case, that we expect early on, the first big finds of hydrogen, you expect the infrastructure to be built close to the point of production. And that makes sense, and that follows history. The reason why all the refineries are in Houston is because that's where the first big oil finds. So the resource was discovered first, and then the processing facilities were put on top of the resource. And then as more resource was found in broader places, that's how the pipeline networks developed. We expect a similar thing to happen. If geologic hydrogen can become as big as we hope it does, we expect it'll start out by infrastructure located close to production, and then slowly you'd see pipelines connecting resources and those things. And then it's hard to say like exactly the timeline that'll go. There's a lot of variables, but that's what we expect. And that's kind of the feedback we're getting from potential customers who would develop SAF plants and ammonia plants partnered to us.
Well, and that was a follow-up question I had. And I'm curious what you would say, how close geologic hydrogen is to commercialization, or kind of establishing sort of this infrastructure as you were just talking about.
Well, I mean, so the bulk of my startup experience, so I've done a lot of startup companies. The bulk of it is, you've got a machine that you're trying to develop, and you're taking it through a pilot scale and a demo scale, and then you're getting ready to build your first of a kind commercial scale. And you kind of have like 2 or 3 years on each of those steps really to go. And you have a pretty good feel for how long it's going to take. With geologic hydrogen, where you've got us and a number of other companies that are out there starting to explore, it's a portfolio approach, and you're trying to spread the risk out and share the risk. But, nobody quite knows when the first big finds are going to happen. We've found some stuff that we think is really interesting. We're still working on trying to understand the commerciality of it. But nobody knows when like that first big eureka moment could happen, right? We're all drilling, we're all looking at different places. I can give you the timeline from when that happens. When you have like really big find, it's probably about 3 years to that being sold commercially. And that's mostly because it'll take 3 years for somebody to build an ammonia plant or a SAF plant next door to you. You could have the hydrogen flowing, and we can drill wells really quickly. Like I could drill all the wells needed to produce a lot of hydrogen on a big reservoir in a year. But the lag time will be building out the infrastructure to buy it. So I think it's sort of, think about 3 years from the first big discovery. We're running a big portfolio approach. We think, in the next 2 to 3 years, we expect to have some big discoveries under our, so, if you add A to B, potentially 6 years to seeing like a lot of gas flowing into something commercial if we're successful.
And I was wondering, as kind of part of that development, that timeline, the role that you see of offtake agreements, kind of in a different industry. Fervo signed a major agreement with Google, for example. So are there any kind of potentials or similarities with what you're doing in geologic hydrogen?
Yeah, absolutely. And look, like lots of people want to get that offtake, right? Everybody wants to have an option. So if we're successful, they're waiting with open arms to take that hydrogen. So we have 6 MOUs signed. We have some binding agreements signed. Very, similar types of customers as Fervo, and very different customers, right? They basically have one customer, which is electricity demand, and hydrogen you can do a lot of different things with. So we have commercial agreements in ammonia, in SAF. We're working on one in power, a bunch of different things. But yeah, we have a lot of that offtake interest. Again, I think that the challenge, right, is that this is early, and there's a lot of capital that need to get put in place to build out the infrastructure. And so we've got to hit certain de-risking milestones on our side to get a partner comfortable and putting steel in the ground to accept the hydrogen. That's a chicken and egg game that anybody who's been a CEO of a startup clean tech company knows that game well. You try to de-risk in time while you're trying to get your partners ready to buy your product. But we're very similar to what they're doing.
And it seems that there's obviously huge investor appetite despite the risk, despite the uncertainties. As we mentioned earlier, Koloma's raised over $350 million. So could you, I guess just to kind of wrap us up, talk a little bit about what you're seeing from investors, why there is such appetite?
Well, I mean, if you just point back to the potential impact of geologic hydrogen, I mean, most of the investors who are investing in Koloma also have investments in such companies, clean energy companies. And when they got wind of what we were doing and, the data sets we had and the head start we had, it was sort of like, this could change everything. This could be a fund maker for the investors. There's not a lot of investments in clean tech that could just go 20 or 30x return. It's just too hard of a sector. So I think a lot of shareholders want to be involved in this and want to have 5 to 10% of their fund exposed to something with this kind of an upside and this kind of an impact. It's not for everybody. Like, exploration risk is different than pure technology risk. And a lot of investment shops are really geared towards assessing, technology readiness levels and what's the tech and are you a pilot or demo? This is the different kind of risk. So the people who are best at understanding this risk are oil and gas investors, but it's a little bit early for them in this one. So right now, primarily we're seeing the interest out of corporate strategics and venture and sort of climate tech venture. We expect in the next 2 to 3 years, as more people get into this space, that we're going to start to see more and more capital come out of resource investors like oil and gas investors.
Well, great. Pete, I think that's all the time that we have, but obviously there is so much more that we could talk about. I appreciate you taking the time, and thank you everybody who tuned in.
Yep. Thanks. Great talking to you. I appreciate it.